Hello viewers, welcome to this next lecture on the NPTEL MOOC course on mathematical portfolio theory. You would recall that in the last lecture we had started talking about the safety first criteria, and we have done one of the safety first criteria, namely the Roy's criteria, which involves the minimization of the return of the portfolio being less than or equal to certain predetermined threshold level. So, in today's class we will continue our discussion on the safety first criteria, and we will look at two new criteria, and we will discuss those in detail and illustrate that through one example each to further our discussion on non-mean variance portfolio theory. So, accordingly we start this lecture with the new safety first criteria, that is known as Kataoka's safety first criteria. So, Kataoka in 1963 developed a safety first criteria and this involves investors choosing the portfolio with an insured return RL as high as possible subject that to the following constraint. So, this means that they want to have as large as possible an RL subject to the following constraint, and the constraint is the following, that the probability that the portfolio return, that means the portfolio that has been actively managed, is no greater than the insured return must not exceed a predetermined level denoted alpha. So, in other words, so let me offer a little bit of clarity in exactly how this translates to mathematically. So, in other words, the problem statement of Kataoka's safety first criteria is the following, that you want to maximize RL subject to the following probability, and the probability is that the probability that your RP being less than your RL is going to be less than or equal to some predetermined level denoted as alpha. Okay, so I will explain this in a little more detail as we move along. So, let us try to reconcile this with the Roy's criteria. So, like Roy's criteria, the Kataoka's safety first criteria can be analyzed from the paradigm of the mean variance approach provided the distribution of the returns can be characterized using only mean and variance. Okay, so let us now introduce the notation. So first of all, let me talk about the notation RL. So this is used to define the insured or denote the insured level of return, right, and you have alpha which is predetermined. So what we do is that we essentially look at the return of the portfolios, and suppose that it is of this form. So it is normally distributed, and I am considering that this is normally distributed for the sake of better clarity. So here what we have, so it is on the x axis we have Rp, so this is going to be E of Rp, and we have a predetermined alpha, and that is given by this shaded area, and accordingly this value on the x axis is going to be denoted by RL. So I can come back to my statement that here this RL level is the insured level of return such that below which the area is less than or equal to this alpha. All right. Okay. So let me delve a little deeper into this. So what we do is that now we relate this, that means the Kataoka's safety first criteria, to the traditional mean variance approach, so accordingly let us consider the returns to be normally distributed. So we have already considered this in this figure, that they are normally distributed. So then what happens? Accordingly we can observe that, so we are interested in the probability of the return of the portfolio being less than the insured level. We want this probability to be less than or equal to alpha. So coming back to this normal distribution, so this means that RL, so essentially the insured level RL is that level such that below which, so beyond to the left of it, the area under the curve is going to be less than or equal to alpha. Okay. So now this coming back to this probability of Rp less than RL is less than or equal to alpha. What does this mean? This means that now if since I have assumed that the returns are normally distributed, that is your Rp is normally distributed. So this condition then reduces to RL minus ERP over sigma p is less than or equal to minus some z alpha, and which implies that, so this is actually implies and implied by that R of L is less than or equal to E of Rp. So from here I get RL less than or equal to ERP minus z alpha into sigma p. Now I have, of course, I have already specified what RL, ERP and sigma p are, but I have not specified what is z alpha. So let me just specify what is z alpha. So accordingly you note that Z alpha is chosen such that probability of Z greater than Z alpha is equal to alpha. All right. So, if you look at this distribution and you have this area under the curve. So, this area, if this is the area is alpha, then this is nothing but probability of Z greater than Z alpha, where this point is going to be equal to Z alpha, and accordingly symmetrically this point here is going to be minus Z alpha. So, that is the reason why we take this Rp minus RL, we can use this expression, and this is going to be less than or equal to minus Z alpha. All right. So, this is the definition of what is going to be my Z alpha. Now, since the investors want to reach the insured level of return at the maximum level, right. Remember, RL is less than or equal to this. So, they want to obviously they want to have the insured level of return to be maximum possible, and since this is the we have the upper bound of that. So, therefore, from the investor's point of view, the insured level of return RL is going to be the upper bound E of Rp minus Z alpha into sigma of P. All right. So, now let us look at this through an example. So, we recall the table where we had these portfolios A, B, C and D, and you remember that the expected return ERP was. So, this is the table I had introduced in the last class. So, for A the expected return is 12%, for B it is 10%, for C it is 15%, and for D this is 10%. And the corresponding standard deviation sigma p is going to be 9%, 4%, 10% and 8%. So, now what you do is we assume that, and again this is for the illustrative purpose, and this argument can be extended to any distribution that can be specified using mean and variance. So, assume that the returns on the portfolio are normally distributed. Okay. So, now let the predetermined level of alpha be 5%. So, this means that you want to find your RL to be as large as possible, while at the same time ensuring that probability of your return of the portfolio being less than this level RL, this should be obviously less than or equal to just 5%. Okay. So, now we have set up this example with these 4 portfolios, and I have specified what is going to be my predetermined level of alpha. So, now what you can do, so accordingly I want to pose the following question, is that amongst these 4 portfolio A, B and C and D, which of the portfolios A, B, C and D would be the most desirable to an investor who is using the Kataoka's safety first criteria. So, let us try to answer this question. So, let us revisit the constraint. So, remember that we have to maximize RL subject to this constraint. So, accordingly the constraint is given by probability of Rp less than Rl less than or equal to alpha implies and implied by probability of Z less than or equal to RL minus ERP over sigma p, right. Since Rp is normally distributed, so obviously Rp minus ERP over sigma p is normally distributed, and I want this to be less than or equal to alpha. Now, since alpha equal to 5%, right. So, the abscissa value or the x axis value for n01 distribution is given by what? This is equal to minus 1.645, and this is going to be equal to the RL minus ERP over sigma p. So, therefore, the insured level of return. So, from this relation we can get the insured level of return is given by the relation. So, from here I get RL is equal to ERP plus 1 minus of 1.645 into sigma p. All right. So, now for portfolios A, B, C and D, what do we have? We will have we need to calculate what is RLA, RLB, RLC and RLD. So, what are these going to be? These are going to be E of Rp. So, what are the E of Rp? So, you go back to the original table, the E of Rps were 12%, 10%, 15% and 10%. Okay, so, we will write those values here. So, this is going to be 12, 10, 15 and 10. And then we have sigma p. So, what are the sigma p values? The sigma p values are going to be 9, 4, 10 and 8. So, this is going to be 9, 4, 10 and 8. So, I have substituted the ERP and the sigma p value, and then I multiply this with minus 1.645. So, each of those terms I factor in the minus 1.645. So, this was actually obtained from the this value of minus 1.645 was obtained from the table for standard normal distribution. So, this effectively turns out to be minus 2.805%. This is 3.42%. This is minus 1.45% and this is minus 3.16%. All right. So, then so that means what? So, that means that since all of them we consider the identical loss of probabilities. So, at the identical level of loss probability of alpha equal to 5%, and I am considering they are identical because I have minus 1.645 in all the cases. The lowest possible acceptable returns for A, B, C, D are minus 2.805%, 3.42%, minus 1.45% and minus 3.16%. Thus we can conclude that the desirability of the portfolios are in the following order. So, first I will have B because this is the highest value, then next I will have C, which is minus 1.45%, then I will have A, which is minus 2.805%, and then finally we have D, which is minus 3.16%. So that means I am basically choosing in terms of starting with the highest highest RL that we get, insured level of return, and coming down all the way to the lowest value, which is minus 3.16%. Okay, now let us see how does this turn out to be graphically. So graphically one can view this like that. So suppose now I have this relation. So with alpha equal to 5%, I have the relation E of Rp is equal to RL plus 1.645 sigma p. All right. So remember here what did we have? We had RL equal to ERP minus 1.645 sigma p. So I will write now E of Rp in terms of RL and sigma p on both the sides, or on the same side. So what are these? These are nothing but, these are some straight lines with identical slopes in the sigma p ERP plane. So if we take the sigma p ERP plane, so these are going to be some straight lines. And then what we have is we have the efficient frontier. So what we have is now that suppose we call this this portfolio say E, F, G, H. So all these portfolios have an identical the slope of 1.645, but the RL, which is the intercept, that is going to be highest in case of this portfolio E, because this has got the highest intercept. And this is just the manifestation of the a graphical representation of the Kataoka's safety first criteria. Okay, so just to sort of elaborate on this, so we just write that we have parallel straight lines through portfolios E, F, G, H in the sigma p ERP plane. So note the following, that the first thing you note that they have the same slope of 1.645, but they have different intercepts. And the punchline is that as I have explained just now, the most desirable portfolio is the one with the highest intercept, namely that is portfolio E, which is the largest intercept amongst all the 4 portfolios. All right. So now that we have done this Kataoka's and Roy's criteria, so we want to now contrast Roy's criteria with Kataoka's criteria, and we make the following observation. First of all, remember that Roy's criteria, it favors portfolios with the greatest slope, but fixed intercept. So recall this from the previous class, and from the discussion that we have completed just now, the Kataoka's criteria gives precedence to portfolios with greatest intercept but fixed slope. So, in case of Roy's criteria, if you have sigma p ERP, you have a fixed intercept, but you will pick up the portfolio that has the highest slope. So, you get a slope, but the intercept is fixed. So, this is the crux of the Roy's criteria. However, in case of the Kataoka's criteria, if we look at the sigma p ERP plane, as we have seen just now, you will have a fixed slope. So, that means you will have identical slope, and then you will pick the one with the greatest intercept, namely this one. All right. So, here the slope is fixed. So, here the intercept is fixed, and here the slope is fixed. So, you basically pick up the one with the highest slope, and here you pick the one with the greatest intercept. So, that is the primary contrast between the Roy's and the Kataoka's criteria. Okay, so let us now come to the last of the three criteria, and that is Telser's safety first criteria. So, Telser in 1955 proposed this criteria, which is based on the assumption that the rational investors maximize. So, it brings us to again the basic motivation for rational investors, that they want to maximize the expected return, but since it is a safety first criteria, so they will maximize the expected return subject to the constraint that the return being less than or equal to a pre-specified minimum level, which will denote by as before RL, has the probability. So, to dismiss that, this is the probability of return being less than or equal to the pre-specified level of RL. This probability will not exceed a given probability. So, so mathematically, how do I present this? So, the criteria is represented as maximize E of RP. Now, what do we want? We want to maximize the expected return, but we need the condition that subject to the probability that the return RP of the portfolio being less than less than or equal to RL. That means, this probability of the portfolio being less than or equal to RL, this is does not exceed some predefined given probability of alpha. So, here note that first of all, you have a pre-specified minimum level. So, here your RL is pre-specified, and it will not exceed a given probability. So, this indicates that alpha is also pre-specified. Okay, now let us as we have done in the other two cases. So, we focus on a situation that if R follows a normal distribution, that RP, that means the return of the portfolio, it follows a normal distribution, then what happens? Then we have So what do we need? The constraint is probability that return of the portfolio Rp less than or equal to n. This must be less than or equal to pre-specified R subscript L. This being less than or equal to a pre-specified level alpha. This implies that you have RL being less than or equal to ERP minus Z alpha sigma p, which implies that ERP is greater than or equal to ZL, greater than or equal to RL plus Z alpha into sigma p. Now, if alpha is equal to 5%, then in particular for this alpha, what we have is ERP is greater than or equal to RL plus 1.645 sigma p. So, accordingly, once I have this condition, so we can make that accordingly the portfolios which satisfy this constraint, the most, so amongst the portfolio which satisfy this constraint, the most desirable in accordance or as driven by the Telser's criteria is the one which has the largest expected return. So this means that basically you want to have this Telser criteria being satisfied, and once this is satisfied, your goal is essentially to maximize this E of RP. So amongst all those portfolios which satisfy this criteria, the most desirable one is the one which has the highest ERP, because eventually according to the criteria your goal is to maximize the ERP. Okay, so now we consider the example again that we have seen earlier. Now, since in this case I need to pre-specify my RL and alpha, so I take my RL to be equal to say minus 2% and alpha equal to 5%. So that corresponds to 1.645. So then what is going to be the ERP in all these cases? All right. So for portfolio A, B, C and D. So you have these 4 portfolios. So what is going to be the ERP? So accordingly, for the first portfolio, so we will enumerate the ERA, ERB, ERC and ERD. All this will be greater than or equal to what did you have? The condition was we had greater than or equal to RL plus 1.645 sigma p. So E of RP is greater than or equal to RL plus 1.645 sigma p. So what is the RL? So RL I have already specified is going to be minus 2%. So this is pre-specified. So accordingly, this is going to be minus 2%. Let me put it minus 2, minus 2, minus 2, minus 2, plus 1.645, plus 1.645, plus 1.645, plus 1.645. Into sigma p. So the sigmas were 9%, 4%, 10% and 8%. So in this case, this turns out to be equal to 12.81%. In the second case, this turns out to be equal to 4.58%. In the third case, this turns out to be equal to 14.45%. And we have the last one to be 11.16%. Now, according to the table, E of RA is 12%, E of RB is 10%, E of RC is 15% and E of RD is 10%. So, now observe very carefully, 12% is not greater than or equal to 12.81%. and 10% is not greater than or equal to 11.16%, but 10% here is greater than 4.58%, and 15% here is greater than 14.45%. So, that even before we can start maximizing the E of RP, we have to check the situations where the Telser's criteria is not satisfied. So, it turns out to be that it is not satisfied in case of A and it is not satisfied in case of D. So, accordingly, we state that here A and D do not satisfy the Telser's criteria, but B and C do satisfy the Telser's criteria. So, now basically we have to choose one amongst B and C. Now, since among B and C has, so it is a 15% return which is higher than 10%. C has the highest or in this case higher expected return. Therefore, C is the most desirable portfolio in the paradigm of Telser's safety first criteria. So, graphically you can see that, so let us look at Telser's safety first criteria without the risk free asset. So, that means since there is no risk free asset, so the efficient frontier would look like this. In the sigma p ERP plane, and then we have this RL, and so basically the line that ERP is equal to RL plus 1.645 sigma p. So, this region is the region where ERP is going to be greater than or equal to RL plus 1.645 sigma p. And this line, so on the top I have the efficient frontier, and this line is what is known as the Telser ray. All right. So, if we have some portfolio Q, R, P, and there is some portfolio S. So, basically what happens is that we have the efficient frontier, and once we set that, bring the Telser ray into the picture, we figure out that S does not satisfy the Telser criteria, and then only Q, R and P satisfies the Telser criteria, and so we have to, the most desirable portfolio amongst Q, R, P is the one that has the highest expected return, namely P. So, we can now summarize this as we consider the Telser's safety first criteria in the paradigm of the mean variance approach assuming of course that the returns are normally distributed and no risk free asset exists. So, I can now make the following statement in the context of this picture that we have here. I can make the following statement, that the portfolios satisfying the constraint given by the Telser's criteria, that must lie in the shaded area, right. The reason I say that must lie in the shaded area, because the this entire area will give the opportunity set or feasible set, and amongst those you can only choose the ones that lie above this Telser ray. So, that means that you can only consider those which are lying in the shaded area as given. So, since the portfolios they are satisfying the constraint, this must lie on the shaded area, and this shaded area is between the constraint and the opportunity set. And so, consequently, the most desirable portfolio is the one with the greatest expected return among the portfolios in the shaded region. So, that means that the portfolios in the shaded region. So, this means that the portfolios in the shaded region are the ones which satisfy the Telser's constraint, and once you have the collection of all the portfolios that satisfy the Telser constraint, you then have to look at the objective of the Telser's criteria, which is maximization of the expected return. So, amongst those which are lying in the shaded region, the most desirable portfolio is going to be the one which has the highest expected return. So, accordingly, if you go back to the figure, you will notice that this is going to be the portfolio. So, you would recall that in that case this is going to be this. So, this is going to be the portfolio P which lies at the top. All right. So, to conclude this, we now consider the existence of the risk free asset. So, in this case what you will have is, we will have again you look at sigma p ERP plane. Now, since we have considered now the existence of the risk free asset, so that means the efficient frontier now is going to be no longer the previous one, but rather the CML emanating from RF, and then the Telser's ray would be going to be given by. So, this is Telser's ray, which is basically given by A of RP, this region, this is greater than or equal to RL plus Z alpha sigma p. So, that means the region above the Telser ray, but below the CML, this is going to be my new shaded region. So, therefore, I can say that the shaded area represents the intersection of the set satisfying the constraint, that means anything that is lying above this Telser ray, and the set and the opportunity set. So, it is the intersection of the region above the Telser ray and the opportunity set, and this intersection is given by this shaded region. All right. So, suppose that we have the portfolio. Suppose that what we have now is, we now have basically this shaded region, and suppose I choose that we find that this portfolio. So, there is some portfolio Q, not to be confused with the Q in the previous diagram. So, suppose that Q is the portfolio. So, I denote by Q the portfolio with the greatest expected return, And what is this going to be? The portfolio, the greatest expected return is going to be on the point of intersection. So, amongst all the portfolios here, the one with the greatest return is going to lie here. So, this portfolio with the greatest expected return, which is at the intersection of the Telser ray and the CML. So, here I identify this with K. So, we make this observation. Now, we say that now what, so accordingly if I identify this with Q, so this may then you have to then, now since this lies on the Telser ray, so obviously it will satisfy the Telser relation of ERP is equal to RL plus Z alpha sigma P. So, accordingly I can write this as ERQ from this relation equal to RL, so from this relation equal to RL plus Z alpha sigma P. So, is equal to RL plus Z alpha. So, instead of sigma P we now have sigma Q. So, this can be written as RL is equal to ERQ minus Z alpha of sigma Q. Now, also remember that Q not only lies on the Telser ray, which is why this condition is satisfied, but also since Q is on the CML, it has weights as a combination of Wm on M. So, remember that any portfolio in the CML can be obtained as a combination of the market portfolio. So, let us say that the weight of the market portfolio is Wm and 1 minus Wm on the risk free asset. So, then what do we have? Then we will have RL is equal to expected value of RQ minus Z alpha sigma Q. Now, since Q is on the CML, so that means RQ is simply going to be Wm Rm plus 1 minus Wm Rf. So, the expected value of RQ accordingly from here, this is going to be Wm E of Rm plus 1 minus Wm into Rf. So, this term is taken care of minus Z alpha. And so, here sigma Q is simply going to be the standard deviation of this term, because this term will vanish and the cross term is going to vanish. So, Z alpha into sigma Q is simply going to be Wm into sigma m. And therefore, what we have is that, so this will imply that Wm is equal to RL minus Rf is equal to E over Erm minus Rf minus Z alpha of sigma m. Alright, so this brings us to the end of today's lecture. So, just to do a recap of what we have done. So, we picked up from where you left up in the last lecture and where we had done the Roy's criteria, and we introduced the Kataoka's criteria and we compared both of them. So, in case of Roy's criteria, the intercept was fixed, and then the most desirable portfolio was going to be the one which is the highest slope, and in case of the Kataoka's criteria, the slopes were fixed, and then amongst the different portfolios with identical slopes, you ended up picking the most desirable portfolio as the one which has the highest intercept. And then we talked about the Ray's criteria, which sought to maximize the expected return given a certain constraint which was given by the relation ERP is greater than or equal to RL plus Z alpha into sigma P. And so, where the probability that your return of the portfolio, so it is equivalent to the portfolio of the return, probability of the return of your portfolio being less than some predefined criteria RL, and you could not let that probability fall below in alpha beyond a certain level. And we looked at the graphical illustration of both these criteria that we discussed together in the context of assuming that the returns are normally distributed, which can be extended to returns of the distribution of the returns being not only just normally distributed, but also it could be any other distribution that relies only on the mean and variance. and then we also looked at a graphical representation of the Telser's criteria. Once in the case where we had the Markowitz framework without any risk free asset, and then in the context of the capital market line when a risk free. So, in the first case no risk free asset was included, it was only risky assets, and in the second case, in case of the capital market line, we implemented the Telser's criteria, and this had to be done in the context of the capital market line. So, this concludes our discussion on the safety first criteria, which was the one of the first topics that we had talked we had dwelled upon when we started our discussion on the new non-mean variance framework. And then in the next class onwards, we will continue our discussion on other non-mean variance approaches in order to optimize our portfolio. Thank you for watching.